Hello, and welcome back to our Design of Experiments Fireside Chat for February. I'm Doug Montgomery, and for those of you that are sort of new to what we're doing around here, and to the idea of our Design of Experiments courses on Coursera, I host a monthly Fireside Chat with a guest speaker, and purpose here is to try to explore specific topics and some applications of experimental design techniques and methods that I think enhance the things that actually go on in the course. We always leave some time at the end for Q&A, and this is a really good time for you to ask questions. And your questions could be about the Coursera courses or any topic that comes up in that course that you'd like to talk about, please do. And if you have a question that is specific to a situation that you're actually encountering or trying to deal with, please feel free to ask that too, and we'll do our best to try to answer that. For those of you that are actually on Coursera, we post recordings of these fireside chats to the courses, and you'll find them in the resources tab of your course. Quick reminder for those of you in the audience, please keep your microphones muted and your cameras off during the session to avoid any extraneous noise or other kinds of disturbances that might be a problem. If you want to submit a question either to me or to the guest, please do so using the chat function on the Zoom menu bar. And you don't need to wait until the Q&A begins to do that. You can start putting that in at any point during the session. And if your question doesn't get answered during this time, we will try to respond to it in Coursera for those of you that are enrolled in the course. I'm really pleased and honored to introduce our guest today, Robert Mee, who is the William and Sarah Clark Professor of Business Analytics in the Haslam College of Business at the University of Tennessee. He got his BS degree in management science from Georgia Tech. And I actually met Bobby Mee when he was a student at Georgia Tech. He was an undergraduate student, and he actually took a course from me, a graduate course, and he just did beautifully. An amazingly smart guy, and he got his MS and PhD in statistics from Iowa State University. He's a fellow of the American Statistical Association. He was on the Technometrics Management Committee for 12 years. And he was an associate editor of that journal for 7 years. And he's currently on the editorial board of the Journal of Quality Technology. His interests include design and analysis of experiments, choice-based conjoint analysis, and he's the author of a really nice book called A Comprehensive Guide to Factorial Two-Level Experimentation, published by Springer. And it is in fact a very comprehensive, very thorough, and a very well-written book that I would highly recommend to those of you that are interested in or using factorial two-level designs. So with that, I'm going to turn this over to Dr. Mee and let him talk about his presentation for today.
Oh, he's muted.
Welcome on this Ash Wednesday. Doug, thank you for the introduction. It was 1977 when I had your response surface methodology class. Your enthusiasm for design combined with the usefulness of the methods is what drew me to statistics in grad school. And it's fitting that today's topic is on response surface methodology. It's new tools that have been developed in the last 12 to 15 years. And this talk is based on a JQT paper. It's co-authored by Mengmeng Liu and Youngdao Zhou, who are both at Nankai University. And Doug has mentioned that definitive screening designs are part of the response surface methodology course module that he teaches in Coursera. So my talk, I'll begin by just describing definitive screening designs. I'll give an example. I'll show analysis of the data from that example, which is going to indicate challenges, difficulties. We'll talk about the weaknesses of definitive screening designs. And then the main point that I wish to stress is the need for augmentation of those designs. The definitive screening designs can function much like two-level factorials do in the context of central composite designs. So I don't anticipate having time for the four-factor projections, something that is in the paper, but I will not necessarily have time for today. But you'll see the main thrust of the strategy of augmenting definitive screening designs. So the definitive screening design idea appeared 13 years ago in a Journal of Quality Technology article, and you can see how many times it's been cited. A year later, an additional paper in JQT emphasized the connection between definitive screening designs and conference matrices. And so I will begin by talking about conference matrices and how the DSD is constructed from that. So you see on this slide, a conference design is an N by M matrix. In the example that you're about to see, both M, the number of factors, and N, the number of rows of that matrix, are going to be 6. A conference matrix has -1, zeros, and ones. There is a single 0 in each column. The other values are plus or minus 1. And the columns of the matrix are orthogonal to one another, so that X prime X is just a multiple of the identity matrix. Conference matrices only exist for an even number of rows. So once we have a conference design matrix, we can create the definitive screening design by folding over the matrix X. So here X is that conference design matrix. Minus X is where we reverse all the columns, and then we append to that at least one run at the center point level. So let's look at an example. So here is that 6 by 6 conference matrix X that you see shaded in gray. And then you see the fold over of that is the next 6 rows. And then finally, here we have a single row of zeros, the center point combination in the last row. Obviously, the runs should not be performed in this order, but it's easy to see the construction from this. The rows ought to be performed in a randomized order. I'll now go through an example. It's a study of 3D printing in the journal Rapid Prototyping Journal. The title of the article is shown there. And there are 6 numeric factors. 5 of those are continuous variables. The 6th one is numeric but discrete, the number of contours. You'll notice in this table 1 from the article, 2 of those center point levels for A and F have an asterisk. And this is because the authors did not choose a level that was exactly halfway between low and high. And so the coded level is not going to be 0. Here is the design, apparently the order in which the runs were performed. You'll notice that there are 4 center point runs, run number 12, and then the last three rows appear to be, it appears as though this is the run order. Although I'm not certain of that. And you see that the actual level, the middle level for A will be coded 0.25, and the actual middle level for F will be coded minus 1/9, corresponding to the levels that the experiment, those factors were set. You see two responses here: creep compliance, recoverable compliance, smaller is better. What models did the authors fit? Well, they fit models for each of these that have linear main effects, a few two-factor interactions, linear by linear interactions, and one or two pure quadratic terms. So these are the terms that would make up a full second order response surface model. This is a subset of those terms. You will see in to the right-hand side, analysis of variance results. In the model for creep compliance, you see lack of fit, 3 degrees of freedom, which means they have left out, they could have had 3 additional terms. They could have had one more main effect. You can see that factor D's main effect is absent, and they could have added a maximum of 2 more second order terms. That would have made a saturated model. So they left out 3 terms. In the second response, recoverable compliance, you can see a lack of fit degree of freedom of only 1. All the main effects were present in their model, and 5 of the maximum possible number of second order terms are also included. These models have very high R-squared, both larger than 99.9%. Well, I'm going to take that second response, recoverable compliance. On the left is the model that the authors fit. And you can see in the standard error for A that it's slightly lower than the standard errors for the other main effects, and that is due to the off-centered nature of the center point. So these are the factors encoded units. You'll see there 4 two-factor interactions and the squared term for F. So I'm going to fit another model. I also have all the main effects. I have only 3 two-factor interactions, and I have F squared. And these 2 models, the one in the paper and the one that I have fit, both have R squared of 99.98%. And the model on the left has AD and CE interactions, which are absent in the model on the right. The model on the right has BF rather than AD and CE. You can see variance inflation factors and how much they are larger among the interactions in the model that the authors chose. So the model on the right is preferred in terms of smaller VIFs. It's a simpler model, same R squared, a smaller mean square error, 636 instead of 741. So my point here is that the authors have overfit this model. There are alternative models that seem to do just as well. Even simpler alternative models that seem to do just as well. But what about predictions from those 2 models? On the top is the model of the authors, and I've used Jump's desirability function where we smaller the better response and ask for that to be minimized. And you can see here it selected the low level for A, B, C, D, and E, and 0.7 for the factor which has the pure quadratic term. Oh my, a minimum of minus 1562 for a variable that cannot be negative. That should have caused the authors some concern about the usefulness of the model that they fit. What about the alternative model that I've proposed? At the combination their model pointed to as optimum, we get a predicted RC value, recoverable compliance, of 673, much more credible. And if I minimize the predicted response from the model that I've fit, the alternative model, I get a minimum of 254. So I am completely sure that the model that the authors fit is inappropriate. Maybe not for the model that I fit. So let's talk about what is a concern here. Our concern is not about precision. If we have an R squared of 99.98%, we're going to have small standard errors. We're going to have lots of statistically significant coefficients. When R squared is that large, the concern is about bias. And recall that there were 4 center point runs. So we have 3 degrees of freedom for pure error, which here there must be negligible variability in those center point runs. But we are concerned about bias. And for definitive screening designs, our concern is about bias to the second order terms. There's an orthogonality. If indeed we had used center point levels, there would be an orthogonality between the linear main effects and all possible second order terms. That's an advantage of definitive screening designs. But the bias that's possible in the second order terms is something that we must recognize when we use a definitive screening design. So what if I have a true model that has columns in this matrix X1 and in another matrix X2, but I only fit a model with X1. X1 is the model matrix that I use to fit, but I have omitted columns of X2. Well, how does the omission of the columns in X2 bias the estimator for beta 1? Well, there is a calculation using a matrix called the alias matrix, which depends entirely on the known matrices X1 and X2. And so we'll call that matrix A. Then the expected value of the least squares estimator for beta 1 is the true beta 1 plus this matrix A times an unknown beta 2. Now, if beta 2 is 0, then omitting those columns has no penalty. And our least squares estimator for beta 1 is unbiased. But the alias matrix shows us about the possibility of bias to the estimates in our model. And so because of the property of orthogonality of main effects, linear main effects, and all second order terms, the alias matrix has zeros in all the rows corresponding to the main effects. But it has non-zeros for many entries in this matrix A for the rows corresponding to second order effects. So let's consider the author's model for creep compliance, the first response. That model had 4 second order terms, AB, BF, C squared, and F squared. And you'll see that I have rows of the alias matrix corresponding to the intercept and those 4 second order terms. Well, they have omitted in their model many second order terms. They omitted all interactions except for AB and BF. And so you see those listed as columns of the alias matrix. And they omitted 4 pure quadratic terms, A squared, B squared, D squared, E squared in this particular model. So I'm showing this matrix A and am alarmed by when coefficients are as large as 1 or even greater than 1. So this says, what is the potential bias to C squared? Well, you can see that those first 4 interactions involving A would produce substantial bias to C squared. Oh, and BD and BE, even more severe bias, meaning that if those interactions are present, we are not seeing a valid estimator for C squared. The same is true for F squared. So you can see the severity of potential bias when we estimate a pure quadratic term. What about the second response that had 5 second order terms, AB, AD, BD, CE, F squared? This was the author's model. And you can see here that, recall their model had AD and CE. Look at the bias from BF. My model had BF in it rather than those 2. And you can see that the coefficient in the alias matrix is 1 in the row for AD and the row for CE. So if there was a BF interaction, then no wonder AD and CE accounted for much the same variation in this model. You can see also that the F squared term in the model actually is essentially estimating the sum of all the pure quadratics, as if we only had a center point in a 2-level design. So my first main message here, don't try to estimate so many second order terms from a single DSD. A DSD is a screening design for second order terms. So here's the full second order response surface model. You can see I have M linear main effects, I have M quadratic main effects, I have M choose 2-factor interactions terms. And under this model, the definitive screening design provides unbiased estimation for the linear main effects. That is a great property of DSDs. The problem arises in the second order terms. So first of all, it is a screening design. There's no way we're going to be able to estimate all the second order terms or even necessarily to recognize which ones are significant. So let's see this in particular. We're going to hope that our experiment can lead us to see which few second order terms are needed. And when we do that, we're going to ignore second order terms in other factors. So here's that response surface model again. If some factors don't have any second order terms, then we can project the DSD into fewer factors. And the good news is, if there are 3 factors that have no second order terms, then I can estimate all the remaining second order terms. That is, in any subset of 3 factors, if those three factors are the only ones with second order coefficients other than zero, then we can estimate that model. And we can include all the linear terms, but just no second order terms involving those factors that we have omitted. So how many terms then are we omitting when we take this design and fit a model with second order terms only in 3 variables? Well, we have m-3 pure quadratic terms we've dropped, and m choose 2 minus 3 interactions that we've dropped. So what does the alias matrix look like in that context? So here is a definitive screening design with 6 factors made from a conference matrix with 6 rows. So 12 runs other than the center point runs. If there are 6 factors, then there are 6 choose 2, 15 two-factor interactions, and we've omitted 12 of those since we've only put in 3 interactions. And we've omitted 3 pure quadratics when we fit the reduced model. So here's the alias matrix. Actually, what you see is double the alias matrix so that I could write the entries in this model as integers. So the largest in magnitude coefficients in this alias matrix are plus or minus 1.5 that you see in the last 3 rows. And so if I take, for instance, the last row of that alias matrix, it tells me what is the expected value of the pure quadratic coefficient for factor 3. Well, it is beta 3,3, the true coefficient for that squared term, but plus 1.5 times 2 betas, plus 1 times 4 of the betas, plus or minus 1 times 4 of the betas, and plus 0.5 for all the rest.
Wow.
And so the potential for bias is clearly present. The potential for bias, if we're wrong in concluding that factors 4, 5, and 6 have no curvature, then you see the potential for bias to the pure quadratic coefficients. Also potential bias to the interactions, but not as severe as the potential bias to the pure quadratic coefficients. So potential bias is one weakness of DSDs. Poor precision is also a potential weakness. Well, no, a certain weakness, not a potential weakness. Here, the rows represent different size DSDs, in from 6 up to 24. So as we go from row to row down this table, we are increasing the sample sizes. And you can see how the variance for the linear terms decreases essentially at a good rate, 1 over n. Or even better, the interaction coefficients also are becoming increasingly precise as we increase the size of the DSD. But look at the variance for pure quadratic coefficients. 0.59 times sigma squared. In other words, these numbers, these variances are roughly sigma squared over 2. Sigma squared over 2. And so there is not the same improvement in precision for pure quadratic coefficients that there is for linear main effects and linear bilinear interactions. So here's a summary of the problems that I need to quickly get to the remedy. Good news, linear main effects are not biased. We can fit a model in any three factors, but the problem here is bias. Bias. So I'm going to remind you, if you've seen response surface methodology before, the idea that you start with a two-level design, maybe a resolution 5 fraction. We add axial points and center point runs and end up with a second order design. These are very popular because they can be built up in stages. The problem is if I have a lot of factors, we rarely start with a resolution 5 fraction. And if we start with a resolution 3 fraction, it's going to be hard to augment that design. And so the second big idea here in this talk is, instead of using a two-level design and augmenting with axial points to get a central composite design, let's begin with a DSD and then augment just as we would in a CCD with an axial block. Here, when we choose the level for the axial points, we can choose alpha of 1, which gives a face-centered cube. Or if we're doing this in 3 factors and use the square root of 3, then we're putting the axial points in a sphere. A sphere with alpha square root of 3 puts the axial points the same distance as full factorial points. This plot shows how augmenting the DSD improves the D efficiency. And I'll pass over other details. So in our example, I would have chosen A, B, and F for the factors to include as second order terms. And this is how we would have done the augmentation. We could have added 6 or 7 runs, 6 axial points and a center point to create a design that would have less bias and better precision. We don't necessarily have to run that many points, but what we show in this plot is that if I just use a coordinate exchange algorithm to augment this model, I don't do quite as well as when I augment with the DSD, meaning these axial points do as well as any points that a general algorithm could find. And so I could have a slightly larger block, slightly smaller block, but I still want to use axial points and center points. I'm going to skip over here I can do something similar if I'm projecting into 4 factors. It's more complicated. You can look at the JQT article to see how that would be done. And again, I'm going to skip over those slides and do the last 2. So what is the point? Definitive screening designs are an excellent choice of screening design if subsequent estimation of the second order model might be desired, as when we are thinking we may continue to build out a central composite design. So the idea here is that the DSD is going to suggest which factors need second order terms, and that we can properly identify those. That's an assumption in what I just showed. But I do believe this will expand the usefulness of DSDs, even if we don't have effect sparsity. This last slide is simply saying that Plackett-Berman designs, 2-level designs of strength 2, are popular screening designs, but they're not as useful in the situation where we want to estimate second order terms. And it's for that context that the DSD does really improve our response surface methodology toolbox. So with that, I'll stop and ask what questions you have.
Thanks very much. This has been a very interesting talk. I had seen the paper, but I learned some things about this that I didn't really necessarily capture right away from reading the paper. This is very, very interesting work, Bobby, and kudos to you for thinking of this.
For those who like using DSDs, I do think this has great potential for not replacing central composite designs, but certainly is seen as a competitor.
Oh, yes, and I think that starting with the DSD gives you a lot more, at least insight from the first set of runs about what what other terms might be, quadratic terms might be of interest. And so I think this is really a great idea. The other thing that crossed my mind here is you mentioned it on one of your slides, is that something like Plackett-Berman designs, always hard to try to figure out how to do augmentation there, because you have the aliasing of main effects and two-factor interactions that cause some issues. But there are other kinds of non-regular designs where it's easier to separate the main effects and two-factor interactions. And so maybe some sort of augmentation strategy like what you're proposing here could be useful with those designs as well.
Yeah, and that's I can take a resolution 4 design, which is going to avoid the bias to main effects, but untangling the two-factor interactions is problematic.
Yeah,
because they're in a regular design fully alias.
Yeah, there are some non-regular designs where you can avoid that complete confounding.
That's right. I could fold over a Plackett-Berman.
Yeah.
And then I'm going to have partial aliasing, partial confounding among the two-factor interactions. So the DSD is going to work if we're not overwhelmed with important second-order terms.
Mm-hmm. Yeah. We've got a question here that says, did you use JMP's augmentation feature for the augmentation process, or did you create a candidate set and use the covariate feature? So I'm curious about your answer there.
So for the comparison of coordinate exchange, that was done in JMP. For the optimal design we did create a candidate set of axial points and center point. And then we did not use JMP. We used MATLAB or SAS, ProcOptex in SAS.
Okay.
So we used a candidate set approach, not in JMP, to show that if we had only 6, let's say I'm going to do an augmentation in 3 factors, 7 runs would allow me to do the 3 pairs of axial points and a center point.
Okay.
6, the recommendation would be just run the axial points. At 5 runs, the recommendation in the paper that we found was, well, drop one of the axial points that's in a direction that's not attractive for one of the factors. So, but the answer is, yeah, we did a candidate set D optimality.
And so it's like a point exchange type.
Yes.
Type method. Yeah. Okay. Well, that seems to make sense, particularly given the fact that there's not many candidate points, so it's efficient to do that.
Yes, that's exactly right. And if you think about the JMP's computations there, if it iterated long enough, it would have to do as well as the candidate set approach.
Yeah.
But it may end up with points that are a rotation where it's messy levels for the factors. And so the candidate set approach that restricts to axial points leads to nice treatment combinations.
Yeah, coordinate exchange can sometimes produce some rather bizarre factor settings that are actually hard to achieve in practice because of the fractional nature of the runs, and that is a concern. And I can see where that could come up here without any big problems. Do you know of anybody that's actually tried this?
No, and I'm hoping that this. So the paper only came out last year. I will be looking for citations and by practitioners to see whether they have used it effectively. But any of your participants listening here to a recording, I'd love to hear what their experience is.
And if I get some questions about this, I will definitely steer them to you. Because one of the things that was really kind of profound interest to me is when those first definitive screening designs were published, 10, 11 years ago, almost immediately, there were a lot of applications that started to appear in a broad variety of journals. Engineering journals from different fields, journals in the biological sciences, just lots of them, and I was really sort of amazed at that at how quickly practitioners jumped on the idea.
Yes, that's not true of all of the design ideas that get thought up.
Yeah, that's right.
Definitive screening designs has been used broadly.
Wildly successful. In fact, I've used one in a project that we have not published the results of this yet because we're still working on it. It's kind of an interesting problem. We don't have any questions that have come in right away. So I'll tell you a little bit about this project because it's kind of interesting. It's a project involving 4 universities. Okay. And it's funded by the Defense Department. And what we're doing is we're developing a diagnostic device that can be used in the field to see whether your troops have been infected by one of what the Defense Department calls the Class A pathogens. And there's like 6 of these, and the one that people are most familiar with is anthrax, but there are 5 others. And normally what you would have to do is you would have to take a blood sample from people and send it to a laboratory somewhere where an assay would be done to see whether they've got one of these problems. And that's not very feasible in situations where you have deployed troops. You need to do this right away. And this device is really kind of interesting. It's not like the test strips that people use for diagnosis. Those are called lateral flow devices because they rely on capillary action to bring the antigens and the pathogens together, but they're not very sensitive. And this is a vertical flow device where we take the sample, and it doesn't have to be blood. It could be any body fluid, and we put it in a device that looks like a hypodermic needle, and you push or inject the sample through this tube, and at the bottom of the tube it goes through a substrate that's got holes in it that are treated with the appropriate antigens. And if any of the pathogens are present, then what happens is you get an illumination at the bottom of this tube, and you can read the illumination with a cell phone. So you could do the diagnosis immediately. And it's a fascinating project. And we've been doing a lot of development work on improving the sensitivity of this. And we've run into a couple of places where DSDs could be attractively used. And we haven't quite gotten to where we're ready to do this yet. But I think when we do, I'm going to get in touch with you, and we'll talk about maybe how we might do this. It's a fascinating project. We're in the process right now of doing some accelerated life testing on the packaging of the materials, because they're going to be, you know, out in the field and exposed to all sorts of temperature and humidity variations. And we need to figure out what the optimum way to package them to prevent failure is.
Yes.
But it is really an amazing project. I've had to learn biochemistry, which
How long have you been on this project?
well, it started about 4 years ago, and we started with the guy who is the principal investigator, the major principal investigator on this is a part of the medical school at the University of Arizona, and I know him because he used to be here at ASU, and he and I had 2 or 3 research projects together that were really successful. And as soon as he got this grant, he roped me into it because he said, I know we're going to be doing a lot of experimental work, and we're going to need help. And so
Nice.
that's been my job on this whole project, has been to work with the other scientists, a little bit with the people that do the pathogen development up at University of Nevada, Reno, and a little bit with some of the people out at Duke that are working with ways to enhance the sensitivity of the antigens that we use. So it's you know, like I say, I've had to learn some biochemistry. Old dogs can learn new tricks.
Well,
Oh,
thanks for telling me about it.
yeah, but and so be prepared. I might be bugging you about about this down the road. Question just came in. Can I have multiple factor levels in DSD models?
Multiple factor levels. So there are these are 3-level designs.
To begin with, yeah.
Yes. And the title of the article was Augmenting Definitive Screening Designs Going Outside the Box. So the idea of, if I choose alpha of 1 for the level for the axial points, then it remains a 3-level design, just like a face-centered central composite design is a 3-level design.
Right.
But if we choose alpha greater than 1, then it becomes a 5-level design.
Right.
And because the precision of the pure quadratic estimates is so poor from the DSD, that there is a great benefit to pushing alpha larger than 1. And so in the article, we proposed using square root of 3 for alpha if I'm augmenting into 3 dimensions, and using alpha of 2 if I'm projecting into 4 dimensions, 4 or more dimensions. Now, obviously, in a particular application, you'd have to consider whether it's viable to push alpha that much larger than 1. But yes, so the idea is a sphere making a 5-level design is recommended whenever that's feasible.
Yeah, that's one of the things that that I think is really interesting about what you've done is you can get some of the same benefits of say a rotatable central composite design because you're spreading those axial runs out beyond the plus or minus one limits, and if that's possible. If that's something that's technically feasible, and it seems like a great idea.
Thanks for the question.
Now we have another one. So as a biochemist, the experiments we perform have very high error between each run. And is there anything I should be paying attention to when implementing DSDs?
You may need more replication.
That's the first thing that occurs to me. Either more replication or some way to reduce the run-to-run error.
Yes, that's right.
And sometimes you can do that with repeat measurements. Not always, but yeah, it's something to reduce the run-to-run variability.
And DSDs can recall that the conference matrix in the example that I showed, N was also 6. There was M was 6 factors. N was 6, which is the minimum number. But if budgets allow, then one could choose M of 6 and N of 8 or 10. In other words, more rows to the matrix. And the DSD literature shows the advantages of doing that.
Yeah, I think I think I've heard Brad Jones call that the fake factor idea.
That's essentially how it's set up in JUMP. That's right.
Yeah, and that always seems to me to be a really good idea if you can do it. Okay, another question. Can you speak more to the screening applications and limitations, assumptions regarding the higher order terms that you mentioned?
Yes. So if I have, in this case, 12 runs besides the center point, then I can estimate six. If I have 6 plus 6 plus center points, then I can estimate up to 6 second order terms. In a screening design, often this recommendation is not more than 30% of the maximum number of terms that could be estimated. That if I think of that 30% rule in this context, that's saying I can define if there's only a couple of large second order terms. And so the idea, just recognizing that usually with a screening design, you don't fit a nearly saturated model because of the confusion of, if I fit a saturated model, I can take lots of different 6 second order terms and get perfect fit, but I won't be able to distinguish which model is correct. And so the idea of, with a DSD, if there's just one or two, with a small DSD, if there's just one or two dominant second order terms, then I ought to be able to find them. If there's a lot of second order terms, the design will not necessarily be able to discriminate which ones matter. But the DSD still can tell me sort of how much curvature there is. And that's useful information.
That's very useful.
That's right. Do the main effects dominate? The linear main effects dominate? If they do, then I'm not as concerned about the curvature.
Right. And I thought that was an interesting question. I appreciate your answer. Here's another one. Now, this is kind of complicated. I'm going to read this and see if we can understand this. It says, I am in engineering applying DSD to surrogate modeling for computer experiments. Okay. I have an M equal 31 DSD. Then use predictor screening, random forest in JUMP to choose M subset, approximately 10 or so. Then I use subset forward selection to fit an RSM. Is this a sensible method to reduce the number of considered second order terms?
Wow, M of 31 has hundreds and hundreds and hundreds of second order terms to screen from.
Right.
So I have no experience with DSDs with so many factors. So I think the rule, when you say a subset of 10, if you're saying a subset of 10 of those 31 factors, that is an enormous challenge. I would not think it would be successful. If instead you're saying recognize 10 second order terms, then that's in the neighborhood of 30% of the number of terms, maximum number that could be estimated. But you said an M subset of 10. To be able to successfully screen out which third of the factors matter, I don't think you'll be able to do that well.
I'm struggling with that myself. I think, but some of these computer experiments do often have very large numbers of factors. It's just the nature of the beast. When people develop a computer model, they tend to put in everything they can think of into the model, and so you do often get lots of factors.
I would ask here: is the simulation so time consuming that you need the economy of a DSD?
Yeah, I might wonder about that myself. Is there a different design strategy that would work? And if the computer model executes fairly quickly, then there's other options that you could look at. But some of these computer models, as I'm sure you know, Bobby, some of these computer models run for hours. I've worked some with, I had a student that did some work in this area some years ago. And the basic model that we started looking at to test some of our ideas, each run took like 2 hours. It was a finite element model, and it just took forever. So, but yeah, that's a good thing. That's an interesting question, and I don't know that I have a terrific answer to add to what you said. We're running out of time. Bobby, I want to thank you very much for taking time out of your super busy schedule to do this. I really, really appreciate it. It's been good to talk with you. I haven't seen you for a few years. You're looking good.
Well, I appreciate the opportunity to pay back the benefit from 40 years ago?
Wow. Yeah. It's been just about that long. Our days together at good old Georgia Tech. Well, this ends today's session. Our next Fireside Chat is going to be March the 20th. That's also a Wednesday. And there's going to be more information about this posted in Coursera as we get closer. And as I mentioned before, you can find the recordings of today and all of our past Fireside Chat recordings in the resources tab in Coursera. And look forward to seeing you back again here next month. Thank you.